Within chemical kinetics, the reaction mechanism refers to the path that reactants take in order to reach our desired products. Now, if we take a look at this example over here, we can note that this overall reaction over here cannot occur in a single step. Instead, we take two steps, which we refer to as the elementary steps, in order to achieve our desired overall reaction and our desired products. So once again, reaction mechanism refers to the path that is taken to reach our desired products. And here, this reaction cannot occur in one step. It occurs in two substeps, and these substeps are referred to as elementary reactions. Now here in my example, we only have two substeps that correlate to our overall elementary reactions. But in reality, you could have multiple elementary reactions, and you would just take the sum of all of the elementary reactions you are given to find your overall reaction. So to find your overall reaction, you take the sum of your elementary reactions. How do you take the sum of elementary reactions? So what you do is that you cancel out reagents, reactants, and products that are the same and occur on opposite sides of the arrow. For example, if this was NO2, you cannot cancel out things that are on the same side of the arrow. You must cancel out things that occur on opposite sides of the arrow. For example, this NO3 there is another NO3 on the opposite side of these arrows, and we're going to cancel out NO3. This NO2 over here also occurs on the opposite side of these arrows right over here, so it's going to be canceled out. So anything that occurs on opposite sides of the arrow and are the same will get canceled out. And then whatever you are left with, you are going to just drag down and you will get your overall reaction. So once again, the reaction mechanism refers to the path that is taken to yield our products. And this reaction cannot occur in a single step. It occurs in two substeps, which are referred to as your elementary reactions. Now, when you look at your elementary reactions, here we only have two, but remember we can have several. When you look at your elementary reactions, you will have reactions that occur at a fast speed, at a slow speed, at a medium speed, and so forth. Now, the slowest elementary step, so the elementary step that occurs the slowest, will be your rate determining step. And why will it be your rate determining step? Well, let's take a look at this energy diagram. So here we have our reactants, here we have our products, and over here we will have our intermediates. Now, let's quickly mention what intermediates are. So intermediates is essentially what is occurring here and over here. It is essentially the middleman between the reactants and the products. Now, remember that whenever we are trying to achieve a reaction, we have the energy of the reactants and we have this energy up here. And the change in these two energy levels refers to as the activation energy. And the activation energy must be achieved in order for a reaction to occur. And in multi-step reaction mechanisms, we have multiple activation energies depending on how many elementary reactions you have. Here we had two elementary reactions, so we're going to have two activation energies. And over here we can see that this first activation energy is a lot higher than the second activation energy. That makes sense because if we take a look up here, our first step was a slow step. Why was it a slow step? Because it requires more energy to be overcome. So whenever you have more energy to overcome, that step will be a lot slower. Thus, your slowest step will have the highest activation energy. And that is why it is referred to as the rate determining step. It has the highest activation energy, and the smaller activation energies and the faster steps will be negligible in comparison to that high activation energy and that slow step. So The slowest step will be the rate determining step, and the slowest step corresponds to the highest activation energy. Now, we've gone over the rate determining step. Now let's go over the rate law. Now, if we go back to our basic understanding of a rate law, we can recall that the rate of a reaction is equal to a constant K times the concentrations of your reactants to some power, and then so forth. And remember, A and B represents the concentration of your reactants. X and Y are simply exponents that can be determined experimentally, and K is just a constant. Now remember that if we are given a overall chemical balanced equation, like we are right over here, the coefficients in this overall reaction order are not representative of the exponents. Now, to make this more clear, let me write out an example. So if I had 3A plus 2B equals C, well, we know that the rate law includes the reactants, so we're focusing on the reactants. C doesn't even matter. This 3 over here, students often mistake this 3 as being the exponent, and this 2 for being the exponent over here, but that is incorrect. The overall balanced chemical equation for a reaction, the coefficients will not correspond to these exponents. But when we are given the elementary reactions, the slowest step, which is the rate determining step, that chemical equation can be used to determine the exponents of the rate law. So let me say that once again to make it clear. The overall reaction, for example, this overall reaction, the coefficients in this case do not correspond to the exponents over here. But if you are given the slowest elementary reaction, those coefficients will correlate to the exponents. So if this equation right over here, if this was your slowest elementary reaction, then you can use these coefficients and determine the exponents. So then 3 would be the exponent over here and 2 would be the exponent over here. But remember, it has to be for the slowest elementary reaction. If you are given the overall reaction coefficients do not correlate to those exponents. Now, we've gone over the rate determining step. We've gone over rate law. Now, let's go over quickly of intermediates. So within a reaction mechanism, an intermediate is a substance that will be produced that does not occur as a reagent in the original reaction. So if we take a look over here, NO3 over here was produced, and it was then not in the final product, and it was not an original reactant. So therefore, NO3 over here is an intermediate. So another way you can remember that is things that cancel out on opposite sides, those are often intermediates. But this does not always apply, because over here we had NO2 and NO2 cancel out. But remember, the key distinction between an intermediate is that it does not occur on the original reactant and the original product side. It is an intermediate must be produced, and it cannot occur on the reactant side, and it cannot occur on the product side. So over here, NO3 was produced in this first step, and then it was used up in this second step, and then it was not produced in the final, so it is the intermediate. Whereas NO2 did occur originally as a product, and then it was produced in the end. And even though it was canceled out, it's not an intermediate. So to figure out your intermediates, the first thing you should do is cross out whatever occurs on the same side, on whatever occurs on different sides of the arrow and is the same. And then take a look if it is produced and then not a part of your original reactants and products. And that is an intermediate. Something also to mention about intermediates is that they will occur in this point of your energy coordinate graph. So here you'll have your product, you'll have your reactants, you'll have your intermediates in the middle over here. and that is essentially reaction mechanisms for chemical kinetics.